So good morning, everyone. This is lecture 7 of memory design and test course. So let's start with a quick review of what we did in the last class. So what were we doing in the last class?
So we saw the bit cell layout,
So then we saw the
80 cell and to read write port.
Okay. So when we looked at the bit cell layout, what were the key features that stayed on with us? What were the most important things that you remember?
the long contacts.
Repetitive behavior.
Hmm?
The repetitive behavior that we
Repetitive behavior, okay, because it's an array.
yes sir.
So the same cell is repeated, but do we simply translate the cell or do we do something else?
Mirroring.
We mirror the cell, we flip the cell, and then what do we do? Why do we need to mirror the cell?
So because we're sharing the metals across the boundary.
Yes, so that we can enable the sharing of lots of whether it is contacts, vias, poly, even source drain region we share across the vertical boundary for the bit lines and the VDD supply. So that is possible only when we flip and only when we mirror. It would not be possible if you would simply translate. If we translate, then we need to keep much more spacing. The full DRC spacing needs to be kept. Okay. What was the next thing that we looked at, or what is the next thing that you remember in the layout of memory cell?
So one was thing that we didn't provide the power rails directly. We cut them and provided with VI3 and then metal 4 for the ground.
So VDD and ground are not provided in every memory cell. So they are there in every memory cell, but the connection to the top level. So in a typical memory instance would use 3 or 4 or 5 metal layers. So power rail would typically be running in the topmost metal layer. Mostly you will see that. So when we have these many metal layers, then power rail from or power connection from that metal 4 does not directly come to the memory cell. So there is no VR3 and no metal 3 stub and no VR2 stub for VDD contact, for example. So where do we get the VDD from? So what we need to do is that in the memory array, after let us say every 32 or 64 rows or something like that, we provide a connection from metal 4 to metal 2 through metal 3. And that is how this chunk of 64 rows gets the VDD supply. This is not just done for the VDD supply. So you remember what is the rule for avoiding latch up? What do we need to do?
P-tap and tap.
Yeah, we have to provide power. I'm sorry, yeah, please repeat.
Substrate connection.
Yes, so we have to provide supply to the substrate at frequent intervals so that substrate resistance does not go high. If substrate resistance is maintained to be low, then we can avoid latch up. So there are rules which govern how far two different substrate connections can be. You will notice that in a memory array, when you have such arrangement, then you anyway need to break the array after 64 rows or 128 rows or something like that. So wherever you are breaking the array for giving these substrate connections, that is also the place where you will connect the power supplies. Is that okay?
Yes sir.
So in the metal 4, sir, actually I had a doubt, sir, but in the metal 4, there were clear rails. In the layout, I saw that in the metal 4, I provided the rails for the power supply. But then you said that we were not providing that power and we are connecting the metal 4 to metal 2, sir. What exactly was that?
We did not show metal 4 in the layout. In the layout that I showed last time, we did not show metal. We only went up to metal 3.
Sir, there was a metal 4 for ground, right?
So
For ground.
That was metal 3.
Sir, for intra-metal capacitance, we did cut that upper part
That was
and we
metal
made
3. That was metal 3. Word line is in metal 3.
Huh,
So what metal were the bit lines then? Chalo, let you tell me this.
Sir, metal 1 only, sir. Bit lines were in metal 1 only.
Bit lines were in metal 1? Vertical bit lines were in metal 1?
metal 2.
Metal 2, I think, sir.
Metal 2, sir.
The bit lines were in metal 2. So if bit lines were in metal 2, then what is the layer that comes after that?
Metal 3, obviously.
Metal 3. So then what was the, what do you say? What layer was the word?
So metal 3 word line and the ground rays required in the metal 3, sir.
I'm sorry, can you please repeat?
The word line and the ground rail we provided in the metal 3.
Yeah, so this is metal 3 that we have shown here. We did not show metal 4 at all.
Sir, actually in last class you made a vertical connection, sir, for ground.
I mean, it depends, sir.
Huh.
I made a vertical connection for ground.
Yes.
Vertical rail for showing
Vertical
that.
rail.
Sir,
Yeah,
you
that
actually
was metal 4. That is what I said. That will be tabbed. That you will so okay. So what we did in the last class was that since we have now disconnected okay, just give me a moment. PowerPoint seems to be playing back. So now since we have disconnected the metal 3 horizontal rail for the word line, what happens is that we do not directly get ground in our layout. And metal and the ground stubs you will notice are also just stubs. In metal 2 they are simply stubs. Even in metal 3 they are simply stubs. So we need to provide power. For that I had probably shown the metal 4 vertical line there, and the connection for ground was provided there, but we did not show anything for VDD.
For VDD, no, sir. We have just taken the substrate connection.
So for VDD, what happens is, for VDD, what we need to do there is, for VDD connection, the connection comes in the strap region. Okay.
So where do I provide that strap region? How I am providing that?
I said na 64 rows ke baad we will give a break into the memory array.
Okay.
After 64 rows, we would give a break into the memory array, and it is there that we would have the connection for VDD there.
Okay, and so that will be, we will be connecting only with the metal 2, right? Because we are providing bit lines there. That will also provide the metal 2, right? For the VDD pre-charge.
I did not get it.
I need the VDD for the bit lines also.
Bit lines. So you do not need VDD connected to the bit lines. You need VDD connected in the IO to the pre-charge circuits.
Yes, acha, okay. Pre-charge circuits. And they will charge the bit line.
Yeah, bit lines will not be connected directly to VDD, na? Otherwise, how will you discharge them if they are permanently connected to VDD?
Yes, sir. So, and one more thing. So, with the basically the word line that will be driven by the row decoder, right? So that will be providing us the charging for this word line, right?
Yes, the word line charge is provided from the row decoder region. Yes.
So metal 3 will be directly connected to the row decoder kind of connection.
Yeah, metal 3 is driven from the row decoder, na? Word line is generated in the row decoder. So
okay, sir.
Okay. So what were the, we looked at two cells, two dual port cells last time. What were they?
So one was one read write, and other was two read write.
Okay. What were the new figures of merit that we looked at?
So in one read write was I partial on.
I partial on was also an important figure of merit that we need to consider. Why is it important?
So because if I'm writing in a mux kind of configuration, then if I'm writing on one and reading on another, then Vx can appear, bump can appear, that could lead to a partial discharge from the the read word line kind of tag and word tag.
Okay, and we still want this thing to be the I partial on to be much lesser than I on, so that
Yes,
I can distinguish easily between a actual 0 and a actual 1 and a partially on 1.
yes, sir. So I had a doubt in this only. So one doubt. So was that key initially with the 60 cells we were sensing the reading by bitline and bitline bar to a differential pair, but only in this we are having only a one bitline. So how am I sensing that? Like any earlier I was sensing amplifier here, what I'm doing.
So you could have an inverter based sensing, you could have single ended sense amplifiers, you could have many such designs. So you can simply use an inverter there, is it not?
So, but that has to be a very skewed in kind of inverter design.
No, it is not necessary. Yes, it will be skewed a bit, but it is not necessary that it has to be very skewed. With a read port, you can actually have, with a independent read port, you can actually have much higher read current there. So you can afford to discharge the bit line to much lower level than a differential pair bit line.
Okay, because I can afford very large read size.
Yeah, so there are multiple ways on how we read single-ended read ports, and you can find a huge range of them in the academic literature.
So, it is kind of that.
Inverter is most commonly used, by the way.
So it is kind of like that the bitline, sorry, the capacitance that was the bitline capacitance that was having, I'm kind of trading off with the kind of the more high current. So I will be able to discharge the high capacitance to this with this high current, and so I can do with the inverter only.
Yeah, I'm giving so much area. I'm adding 2 additional transistors. I'm giving so much extra area, so I'm gaining in speed.
Okay, sir.
Okay. So then we looked at these 2 cells, and we said that there was a homework that you guys had to do. The homework was on estimating the bump voltage and also estimating the constraints around writability. So how many of you were able to do this homework? You can just raise your hand or put a +1 in the chat window. So that's about 1/3 of the class that is here. Okay. So thank you guys. It was important that you do this homework. I actually therefore gave a gap. I could have easily covered this topic in the previous session and not gone to layouts directly. I gave a gap essentially because I wanted that you cover this or do this homework yourself so that you understand the intricacies of memory cell design and the memory assist schemes that you were talking about. Those assist schemes have also been asked in your review quiz, and that review quiz was made with an intent that you would do the homework and understand why different assist schemes operate the way they operate. Or if you need to define a new assist scheme, what can be the basis of that? Now, those of you who did, great, good guys. I think it must have been good learning for you. And those who did not do yet, I would recommend that even though I'm now covering this topic in the class, I would still recommend that you do it. Okay, it's important for your understanding of memory cell operation and how assist schemes help in how assist schemes actually help in uh, increasing density or low voltage operation or stuff like that. Okay, so yes.
Sir, actually, you said na ki you can use any types of parameters. So I also use channel length modulation, and the equation of the read operation will become in the cubic domain, which
Okay.
is very complex.
Yeah.
And sir, yeah. So if I want that, I do not consider the channel length modulation, that the equation will be changed to quadratic form.
Yeah.
So
So
But
see,
sir, realizing all these things with some kinds of equation and estimating that which factor is increasing in how much amount is very difficult.
yes, that is why we need simulators.
Hmm.
See,
Yes,
till
sir.
the time when these short channel effects and other things were not in picture, people used to design by these first order, second order equations only, right?
Yes, sir.
When these additional effects started to come into picture and they started to impact circuit behavior and performance, that was when it became important that we use simulators.
Yes, sir.
So we will go to using simulators also later. Don't worry. We will go to using simulators also. But as of now, let us just have a quick look at what this means in terms of. So just give me a moment. I'm pausing the recording for a little. My PC is giving some trouble. So what we are now doing is we are looking at how to estimate this read bump. So first we just make this we just make the structure of the bit cell where we have M1 and M2, the pass gate and the pull down devices. The pass gate and the pull down devices. Wait. Yeah, we have the pass gate and the pull down devices. And we say that the pass gate is in saturation region of operation. So we say the equation we just look at the first order equation over here in this particular analysis as of now. And we say, okay, that is the equation 1 by 2 mu n C ox W by L of M1 into VGS. So VGS over here would be VWL minus Vx minus Vt, okay, the whole square. So that is the current that you will get from the pass gate, that the pass gate is sinking. The current that the pull down is sinking is in the linear region. So we use the equation as mu C ox W by L, and we go to VRA minus VSS, which is VGS minus VT for the pull down into VDS for the pull down minus VDS square by 2. So this is the equation that we use for the current through M2. Now by Kirchhoff's law, we understand that the current from IDS from M1 is equal to IDS from M2. By equating them, we get this. So what I've done in between is I have simply put CR. I have introduced a variable called cell ratio, which is W by L of the pull down divided by the W by L of the pass gate over here. So when I equate the current from the pull down to the current from the pass gate, I get a quadratic equation. Now, since I'm not using these second order effects, I'm getting a quadratic equation. As we just discussed, you go to more accurate modeling, and you can go to cubic equations, and you can also go to fourth order and fifth order equations, depending on which all effects you want to consider in your analysis. So since we have a quadratic equation, we simply look at what is the A of this quadratic equation, what is the B, what is the C, and we estimate the solution as minus B plus minus B square minus 4AC by 2A. So given this, we arrive at the solution for Vx, which is in this kind of a quadratic form. Are you able to see this? This looks complex, but you will see that when you just go and solve it, it gets solved. And looks cumbersome, but not really a big problem there. Okay? So I think those of you who have already solved it have already done that. Those who have not done it, you anyway need to do it, and it's better that you do it, and then we discuss more about if you have any questions in the office hours later. Let us look at what this means in terms of a memory cell. So how many of you, I'm just curious to understand, how many of you, those who derived these equations, went ahead and saw the impact of changing different voltages, changing different threshold voltages, changing different variables to see what is the impact on Vx? How many of you were able to do that, or did you do that? You can put a +5 in the chat window if any one of you did that. No one did it? Okay, so let's look at yeah, good, Raghav. So at least you did it intuitively. What we can also do is we can just write this equation as in MATLAB and run experiments. You can run as many experiments and you will get interesting results. So let me take you through a small journey of the impact of different things on Vx value there. So let us look at the impact of cell ratio first. What we are assuming over here is, in this first order set of equations, that VTH of all the devices is 300 millivolts. That V array is equal to V word line is equal to V bit line, which is 1 volt. That VD sat is equal to 150 millivolts. That's the standard, 6 kT by Q is what is considered to be VD sat regularly. And that we keep a cell ratio of 1.5. So when we do that, we notice that Vx or V bump comes to be 82 millivolts. Now, if I change the cell ratio to 1, V bump rises to 119 millivolts. So if V bump rises, what happens? What FOM degrades?
Stability.
Degrades.
SNM degrades. Immediately SNM degrades because now you have lesser noise margin there. Okay. Now we say we went to a still bigger cell ratio, and you see V bump reduced so significantly. So that is why, but when you go to a cell ratio of 3, you also increase the area too much and not really desirable. So we keep a cell ratio between 1 to 1.5 in very high current cells, or where we really want low voltage of operation, we can go up to 1.75. Typically 1.75 se zyada cell ratio is avoided in a memory cell. Otherwise it has a much larger area impact. You would rather increase the memory cell current and increase the pass gate a little more. So what is the impact of mismatch? So in the previous case, we had assumed that VTs were all equal. Now we want to see what happens if the VT of different devices changes. We've kept the other things as constant. We are using cell ratio is equal to 1.5. In the first case, we know that when all the VT of all the devices was 300 millivolts, V bump was 82 millivolts. Now let us say that the pass gate is manufactured fast. Pass gate has lower VT. And we also say that the sigma, the variation of VT, the sigma of that is 30 millivolts. So 3 sigma passed a faster pass gate means the VT of the pass gate would be how many millivolts?
210.
210. So when we kept the pass gate VT at 210 millivolts, we saw that the bump increased to 95 millivolts. So this is almost, so not exactly the same, or at least the same trend as you degrade the cell ratio. You made the pass gate fast. So the cell ratio in a way effectively reduced and V bump increased. If simultaneously the pull down was towards slow, So what will be the VT of pull down then? Again, 3 sigma slow pull down.
390.
390. In that case, the V bump went to 109 millivolts. And if you say, so if you have these two variables, pass gate VT and pull down VT, and you say that one is 3 sigma away, the other is 3 sigma away, then in essence, what you have done is you have created a memory cell, which is something like 4 point something sigma away, 4.2 sigma away. 3. So because in probability, if you realize these are independent variables, so they will be orthogonal to each other when we represent them on a graph. And the effective location of my point of my memory cell would be around 4.2 sigma away. 4.2 sigma away means I'm talking about 10,000 memory cells or something like that order. But in reality, I would have memory cells which would, or a memory array or on-chip memory capacity, which would be of the order of megabits. So when we have huge memory capacity, I need to qualify larger sigma extent. I need to possibly go up till 6 sigma. To go up till 6 sigma, I will need to go up to around 4.5 sigma on these axes. Okay. If I do that, if pass gate is 4.5 sigma fast and pull down is 4.5 sigma slow, then with a cell ratio of 1.5, I already have a V bump of 126. Do you remember what was the V bump when cell ratio was 1?
So 119 millivolts.
119. So keeping a cell ratio of 1.5, variations have actually exceeded the impact of keeping a good cell ratio. Now, if I had kept the cell ratio of 1, we looked at the layout and we saw that in that case, the sigma value would reduce. So what has happened over here? The sigma of the pull down is, the VT of the pull down is 450 millivolts. 450? No.
35.
435.
435. And the VT of the pass gate is?
Sir, 165.
165 millivolts. Because my sigma was 30 millivolts there. If I use cell ratio to be 1, probably that sigma would reduce to 20 millivolts. And these are just hypothetical numbers as of now. If it is reduced to 20 millivolts, what happens to this? This goes to
390.
390. This goes to 210. Cell ratio of 1, VT of 290, 210 and 390. You may find that V bump is probably the same value or slightly lesser. At least that on silicon we observed that SNM was better for cell ratio of 1, simply because mismatch had reduced. Are you able to see why mismatch and how mismatch impacts stability of a cell? Any questions?
Sir, this is for the worst case, right? If you reverse like PD, fast, and PG, so it will reduce the bump.
Yeah, but as a designer, what do you want to design? Do you want to qualify the worst case, or you want to be happy about the best case?
Worst case.
Yeah, that is why we're talking about the worst case, Moin. Yeah, this is the worst case, but the worst case has to be qualified, na? That is why.
So why I have need to qualify 6 sigma, sir?
So if you look at the Gaussian statistics, we will look at the statistics part a little later in the course also. But if you look at the Gaussian statistics, you will see that for getting good yield, 99% yield in a 16 megabit array, you need to qualify around 6 sigma variations. Okay. So you remember we talked about what is the coverage. If we have if we have a Gaussian, then within 1 sigma there are this cells are covered, they are qualified. 2 sigma, a still larger extent is qualified. 3 sigma, still larger extent is qualified. Remember we discussed this?
Sir.
Huh? So if I go to 6 sigma, I qualify more cells. And you will notice that 6 sigma means I'm able to get a 99% yield on a 16 megabit array. How much memory, how much cache does your system have? Does your cell phone have? Application processor in the cell phone have? Do you know? Have you checked? L1 cache or L2 cache on your application processor? Not checked. Just go and Google the application processor name of your phone, and details will be available there. So you will see that typically on-chip memory capacity, including L1 caches, L2 caches, and so on, of all the cores and of the remaining part of the chip, for digital SOCs, it is actually very high. It could be 64 megabits in the most advanced technologies today. So 6 sigma is the bare minimum that you need to qualify for SRAMs.
Okay. So I had a thing to ask. So for example, you're seeing with the mismatch, when we have cell ratio of 1, then by a statistical analysis observation, we can see that the V might slightly decrease. So, but like as a designer, I only have the cell ratio in my control. The VT mismatch is not in my control.
Yeah, you
So,
can't. Yeah.
So as a designer, I should be designing a cell ratio of 1.5, right? Because
yes. So only when you are working closely with the technology team, which can only happen when you are working with an IDM. What is an IDM? For example, you're working as a designer in a company like ST, who has its own fabs and who can decide what the memory cell is, or Samsung, or Intel, or TSMC. Then you can do that. But if you're working at ARM or if you're working at Synopsys, where you cannot really request an extra model for a regular, for a cell ratio of 1 kind of a memory cell, you cannot really request a specific spice card which has reduced variations models inside it. You cannot do this design. And even in IDMs, this is usually done by the process teams, technology teams themselves. A designer would not get to choose a cell ratio of 1. Until the technology teams is convinced that yes, they can manage it, they will not open the possibility for the design team. But you should know.
So as we are getting the V bump similar to the cell ratio of 1.5 for the cell ratio of 1 after the considering the variations.
No. With a cell ratio of 1.5, I'm ending up with the same V bump or worse V bump than what I would have got with the cell ratio of 1 when variations are considered.
Yes, so the V bump to same hai hamara, almost similar hai for cell ratio 1.5 and cell ratio 1.
No, 1.5 with mismatch and 1 without mismatch yet.
Okay. Acha, okay, sir, understood.
With the cell ratio of 1, if you put mismatch, you will see there is a loss of bump there also.
Okay, sir.
Okay. So what is the impact of supply voltage? Again, now we say, okay, we are going to that worst case setting that this mismatch is already built in, that cell ratio is 1.5, VD sat is this, V array is equal to V bit line is equal to V word line is equal to 1 volt. So we found that the bump was 126. If I increase the voltage, the bump reduces a bit. If I reduce the voltage, the bump increases. So as I go to lower supply voltages, my static noise margin degrades very significantly. Okay.
Sir, in this slide, we are basically looking at the impact of VARR, right? Because
yeah, as of now, we have kept same voltage on the word line, the bit line, and the array.
So, but like if we reduce the VAR, for example, the supply of the positive, we will see that the bump will increase. But if we also reduce, but independently, say suppose we reduce bit line, then that helps us stability. So I mean, like
Yeah.
because
So let us look at that. Let us look at word line, and then we will also look at bit line. So what happens when word line voltage is changed? What happens then? Let us look at that 0.7 case. Now, everything was at 0.7. My V bump was 162. I reduced word line voltage. My V bump went to 118. I reduced it further. V bump went further lower. So what do we mean by this? That word line underdrive is a read assist scheme. Word line underdrive will help us to improve stability of the cell. But what is the impact? What is the penalty of word line underdrive? Quickly.
Read
the
current.
right,
Cell
the,
current.
the,
Yes, the cell current goes for a toss. Now the pass gate does not have sufficient strength to sink any current. My cell current actually goes for a toss. My memory speed goes for a toss. You're able to see this?
So one thing I need to ask is that while reading, we are looking at two kind of things. One is the cell current and one is stability. So when I say the read assist thing, so I would be basically targeting the stability thing, the VX.
Not necessarily, Raghav. So you may use two assist schemes in parallel. One assist scheme recovers stability, the other recovers cell current.
So, but
If you go on my Google Scholar page, you will see one of my papers where we actually use multiple read assist schemes in parallel to do exactly this.
okay.
Okay.
I mean, sir, for example, I'm able to do something and improve any of the parameters, either the cell current or the stability, I would call it as a read assist.
Yeah. It is assisting. Otherwise, I would have to use larger devices. No? So anything that I'm using to avoid increasing area by electrically modifying stuff, that is assist scheme.
Okay, sir.
Okay.
Because to me, it seems to be contradictory because both can achieve, but I will look into that.
Okay. Now, what is the impact of VSS? So, abhi tak we were always considering that it was ground. Now, let us say VSS is negative. So, you will see bump goes lower. If VSS is positive, the bump would go still higher. So, negative VSS could also be an assist scheme that you could use in memory arrays for improving stability. What happens when you have a negative VSS? What happens to the read current there?
Increasing.
The read current would also increase. See, essentially all that you're saying is if V bump is reducing, then the VDS across the pass gate has increased. So read current would improve. Huh?
Yes, sir.
So can you please repeat the statement?
So if I've reduced this V bump, reduce the level of Vx, what happens to the read current? What happens to the voltage across the drain and source of the pass gate?
It
So
will
it
increase.
increases.
The difference will increase. Yeah.
It increases. What happens to the VGS? That also increases. Huh? So we see an improvement in read current. Okay.
So, sir, I have a question on that.
Yes.
So can you go back to the previous slide for
Yes.
VSS?
Mm-hmm.
So when I was doing this, I coded the equations in Python and then I was entering the values. So for like minus 0.01 VSS, I was getting a very negative value. So sir, if my value is essentially, let's say for V bump, I'm getting in the order of 0.007 something, and then for having a negative VS, I get minus 0.5. So in magnitude
Something
sense,
has gone wrong in your equation, in your model.
yeah, maybe because of certain constants or something.
Yeah.
But I just want some sort of an intuition, like having a negative value which is really high in magnitude. Does that really help us? Like, do we say that we have actually managed to reduce Vx to a better stable point if we are getting a negative value which has a higher magnitude than a positive value?
Yeah, see, if it is, look at it like this. If it was minus 20 millivolts, minus 50 millivolts, minus 70 millivolts at the Vx, now to be able to cause a flip, you will have to bring in more noise, no?
Right.
So that helps. The problem is something else here. When we go to these negative voltage levels, then while over here I'm doing the analysis at 0.7, suppose I have to generate this negative voltage at 0.7 volts. How would I generate that? I would do some charge coupling. I would put in some capacitors. I would toggle those capacitors in a particular way so we'll look into this detail later also. We will generate some negative voltage on the fly. Okay. As I go to higher voltage, let us say 1.0 volts. If at 0.7 volts, I generated minus 0.2 volts. At 1.0 volts, what is the kind of voltage I would generate through those same couplings? 0.3 volts, 50% higher, 0.7 से 1 पे गए, तो उसी ratio में the negative voltage would also increase. So now what is the voltage across the different devices? The voltage is 1.0, which is on the gate, let us say, and minus 0.3, which is on the source or drain. So across the gate oxide, the voltage now is 1.3 volts. As you increase the voltage across the gate oxide, the reliability of the device starts to degrade. That is what actually limits what kind of negative voltages we can use inside a memory.
So VSS is on the source of the pull down, right?
Yeah.
So having I mean, what I meant to ask is that V bump is equal to 37 millivolts and V bump is equal to minus 55 millivolts. So which is the better case out of these two for stability?
So that I already answered. Minus 55 is better.
So even though it in a sense that we are having a more noisy voltage at Vx point, because magnitude wise still 55 millivolts is away from zero. So are we just comparing which is big, like what is the voltage drop across the
Why
path?
did you use the term noisy, Samaksh?
So because
What do you
I'm
mean by
thinking that
noisy?
I'm considering that Vx should be as close to zero as possible and not
That is
as
your
low as
assumption.
possible.
No, that is a wrong assumption.
Based on, okay.
That is a wrong assumption. It is just for ease that we say that this particular voltage is 0 volts. Do you realize the entire chip, for the entire chip, I may keep VSS at 12 volts and VDD at 13.2 volts, and my
Right.
circuit will work perfectly fine.
Yes.
So all this is just about using something as a reference voltage.
Okay, sir. Got it.
No, VSS is just about a reference voltage. When you just, for your ease of calculations, you want to keep that reference, or you want to call that reference voltage as 0.
Okay,
Are you
sir.
able to see this?
Yes, sir.
Otherwise, the entire chip is floating somewhere. We don't even know. We are doing all this analysis with the reference of VSS. Now, what we said is, I will take it lower than that reference. I can do that. Hana?
Yes, sir. Yes.
That is what it is.
Sir?
Yes, Raghav?
So, in this impact of VSS level, I'm getting a little confused and I'm seeing two different things happening. One is that V bump is decreasing. So I can say that it is kind of a stability kind of point of view. It is good also. But as we said that the VD is also increasing. So my cell current is also increasing. So both my merit figure of merits kind of say are increasing. Let's say are improving with the 3 days scheme. I can say that.
Yes.
Okay.
Now the question is, what is the capacitance of VSS? Can you really take it to minus 2 volts? What kind of power consumption will be, what will be the power consumption just to take it to minus 0.2 volts?
The capacitance I can link with the point. Capacitance, I mean.
See, you are not keeping it at minus 0.2 volts always. Now, only during read cycles, you will take it to minus 0.2 volts.
The VSS.
Yeah, VSS. Yes. So there is some charging or discharging that you need to do.
Okay.
That is power consumption.
Okay.
So You need to estimate what is the kind of power consumption or what is the kind of overhead that you are paying for any assist scheme.
Okay.
So yes, if you have a very controlled VSS, a very small capacitance on the VSS, very small in terms of not femtofarads, but yeah, not a huge capacitance on VSS, then you can do this. It may be power efficient. If not, then taking the entire memory array in every read cycle to minus 0.2 volts, it's a huge power consumption. So you may not be able to use the technique.
Okay.
Sir, why can't we put it to minus 0.2 all the time? Actually?
Just let me finish. So you will notice that in academic literature, you will see many people are proposing such funny schemes without really talking about how to implement VSS in a manner that the voltage of or the capacitance of VSS is low enough. Okay. So Faisal was asking, why can't we keep VSS at minus 0.2 volts always? So then that is almost as good as operating the memory at 0.9 volts. Then why generate a negative voltage in the first place? Just use 0.9 volts. If VSS was always minus 0.2, then it is as good as operating at 0.9 volts. No? That is the kind of power consumption. You are switching every capacitance between minus 0.2 and 0.7. So why then call this reference as minus 0.2? You call the reference as 0 and call the VDD as 0.9. That is the power consumption you're talking about. Are you able to see this? Faisal?
Sir, actually, I didn't understand, sir. That was me.
So why do you want to go to lower supply voltages? Let's start with this basic question.
Lower supply to reduce leakage, sir, actually. So
Only leakage?
In this, we are
doing
going
read and write
lower...
here. I'm doing read and write here. Am I worried about leakage when I'm doing read and write?
No, sir. Over here, the bump voltage is getting reduced.
Oh, so you think I will reduce voltage of operation for reducing bump voltage in a memory cell?
Sir, to increase VDS.
So I want to
Sir,
make
to
my pull
increase
down,
VDS.
the pull down
Why
strong.
do we do voltage scaling? You remember we talked about dynamic voltage and frequency scaling. Why do we do that?
The power efficiency, because I want to modulate my depending on my frequency of operation. I want to save the load.
We saw that when the load is not very high, let me not consume too much power. Let me operate slower and let me go to a lower voltage. So the entire attempt of going to lower voltage was to reduce power consumption. Am I right?
Yes, sir.
Yes, sir. Yeah.
If power is not reducing, then what's the point in going to lower voltage?
Sir,
Now you are telling me that always keep VSS at minus 0.2. So what is the voltage swing that you are having on all the capacitors now? Instead of 0 to 0.9, they are swinging between minus 0.2 to 0.7. Is the power consumption reducing?
No, sir.
No, sir. No.
Then why? This is not even a scheme then, no?
Yes, sir.
You only do this in the read cycle, only in that limited part where you are doing read operation. Everywhere else, everything is 0.7. Only where you're doing read operation, there you have done this voltage boost or negative VSS, and you recover the performance, you recover the functionality. Everywhere else, it is lower power. That is when you will gain some benefit. That is where it is called as an assist scheme. Okay?
Yes, sir. Thank you.
Yeah. So now if we add mismatch or look at mismatch in the presence of high VT devices, let us say a memory cell, we want to use a high VT memory cell so that leakage is lower, then you will see the bump would increase further. Memory arrays, if you remember even the example that we have done in the DVD course, memory arrays are usually designed with high VT devices. So when we use a high VT device, we see bump increases further. Okay.
So in this, I would be needing more assist schemes. with the VT kind of high VT devices.
Yeah. So high VT devices, you see that the effect of mismatch increases still further. The impact of mismatch is still higher. Okay. So let's also similarly look at the right estimation. What happens in the right operation? So we looked at the read operation first. Now we look at the write operation. Over here, we make these 4 transistors there. M1, M2 were already there, where we say Vx has appeared, and we also now add the other side where where 0 is to be written. Vint needs to be discharged. Now you say a good write operation has happened when Vint has gone as close to 0 as possible. Are you with me? A write operation has happened when Vint comes to as close to 0 as possible. Okay. So now again we simply do the Kirchhoff's law. We simply apply Kirchhoff's law. We say the current coming from M4 has to be sunk by the right driver, and the current going from M3 has to kind of also discharge Vint. So IDS M4 and IDS M3 equations are written. We define, just like we had defined cell ratio there, we define pull-up ratio there. The size of the M4 is the pull-up upon the size of the pass gate, and we again arrive at this quadratic equation. When we solve the quadratic equation, this is what we get. Okay, so again, those of you who have not done this analysis, I would strongly recommend that you please do this. I'm not solving this for you. I'm just showing it to you so that you can do this at leisure and get a better understanding of what happens during the write operation. So now with that equation, we again do the same kind of variations. What is the impact of pull-up ratio? And you will see that when pull-up ratio is very high, or when pull-up ratio goes high, then Vint rises. It means I'm not really able to write into the memory cell. When I keep a still weaker pull-up ratio, my Vint goes still lower. We keep a pull-up ratio of 0.5 for further analysis. And now introduce mismatch. You will see that with mismatch, as expected. So what we have done, we have said that pass gate is slower. See, what did we want? We wanted pass gate to be faster. Pass gate is faster means pull-up ratio is small. So for the worst case analysis in the presence of mismatch, we put pass gate at 3 sigma slow. We see Vint rises from 30 to 40. You increase the VT of the pass gate, and you also put increase the VT of the change the VT of the pull up, and you see this goes still further. So the system is degrading. In terms of supply voltage, what do you expect? As I reduce the supply voltage, will writability improve or degrade?
So it should improve, sir.
It should improve. Why?
Sir, if I'm lowering the supply, then the pull-up is becoming weak, sir. And if my pull-up becomes weak, then my writability of 0 will improve.
So if I reduce the supply voltage, you will see it degrades because my pass gate now also sinks lesser current.
Sir,
see, pull-up is in saturation region.
Yes, sir.
Pull-up is still in saturation region. Pass gate is in linear region. As you reduce the supply voltage, pass gate goes into still more resistive mode. Pull-up is still operating in saturation. So my Vint actually increases. You see, Vint is lowest when VDD was 1 volt. Even at 1.1 volt, VDD degraded, Vint degraded. So the trend that you're talking about, that trend is right when you're talking of going to a higher voltage. But as you go to lower voltage, the second parameter, which is the current being sunk from the pass gate, that comes into picture. and that degrades the setting. Okay.
So I mean, I'm not able to get it that while with increase also I'm degrading, with decrease also I'm degrading. So
Yes,
hmm,
that's the challenge of a non-CMOS ratioed kind of a design. You could experience that stuff.
so
So there
sir,
is a sweet spot.
when I'm saying the supply voltage, I mean to supply means all the word line bit like you are
Yeah,
erasing everything. So
everything.
here, so sir, here though my pull up will become weaker, but the reduction in the pass gate is more, matlab is dominating here. It is kind of that.
Because see, the pass gate was never operating at its full strength, na? It was in
Yes,
linear
sir.
region,
Yes, sir. Yes, sir.
है
Okay.
ना? So
Okay.
that is what you need to see. What is in linear region, what is in saturation region. So the impact is like this.
Pass gate degrade more.
Yeah. So what happens when I simply lower array supply? Do not lower the bit line and word line. So you see
Then
that
it
was
will.
63. I lowered just the array. I saw an improvement now.
Okay.
This is where pass gate has not degraded now.
Okay. Yes, sir.
This is where only the PMOS has degraded. Are you able to see this?
Since we are not varying the word line voltage.
Yes.
Okay. Yes.
So VDD lowering, but not lowering word line and bit line is a write assist technique. What goes for a toss when we do this? Quickly.
Right time.
Right time. है ना? Because your pull-up has become so weak, now right time goes for a toss. You're able to write, but it takes much longer.
But
Now
I will
let us,
call this as, but I will call this as a right assistant, right?
it is a write assist, yes. Okay. Now let us look at the impact of word line. So again, as the word line is raised, so I have kept array and bit line both at 0.7. I simply raise the word line. And you will see I see an improvement. So word line lowering was a read assist scheme. Word line raising is a write assist scheme. So if you are in Mux 4, can you use word line raising as a write assist scheme?
So it will have some issues, sir.
Yes.
Yes, sir.
Because word line raising would degrade the stability of the adjacent memory cells. You cannot really use word line raising or word line boost as a write assist scheme for higher mux configurations. You can use it in mux 1 though. So the paper that I was mentioning to you about, where we use multiple read and write assist schemes in parallel to go to very low voltages, in that paper you will see that we are doing something of this sort. We are using word line boost. We have a physical mux 4, but we have an electrical mux 1. So just go and check out that paper. It's a very interesting paper. Okay. Now let's look at the impact of VSS. So you will see that when VSS is raised, what happens when VSS is raised? Vx rises. As Vx rises, my writability improves.
So writability was increasing, sir. Yeah. So my writability is decreasing.
Writability improved now because this voltage lowered from 63 to 53.
Oh yes, yes, yes.
Writability improved, but when I raise the VSS, what degrades? The stability of the cell degrades. So again, if I'm able to change VSS, see the layout that we just saw, how was the VSS there? The layout that we just saw, we said VSS is going, is connected on these two adjacent memory cells have the same VSS, and there is a metal 4 which would connect to this VSS. So if I change the supply of a particular metal rail, the adjacent cell supply also degrades. I need to take care of what happens to the stability of this particular cell now. Are you able to see this?
So, but even the stability of that cell also will degrade, right? Because
See, you are writing into this memory cell. So either ki stability degrading is what you want.
yes,
It is the adjacent cell which we are worried about,
yes, yes.
which was in read mode. Now, what happens when we use HVT devices and stuff like that? We see as we go to HVT devices, the Vint actually increases. So V bump nahi hai, Vnt hai. This is a typo. I will correct this later. Okay. So writability degrades. So high VT memory arrays are used on a regular basis, but when you use high VT memory arrays, both readability and writability degrade. Okay.
सर अपने वर्स्ट केस देखेंगे ना हम, तो इसमें इन्होंने नीचे पीजी को फास्ट क्यों कर रखा है? पीजी को स्लो करना चाहिए था ना यहाँ पे.
हाँ, ये वो actually this was ये V bump, this was slide copied from the read part, so that is where it has gone. I will correct this. Thanks for pointing out. Okay. So please do this analysis. If you have written the equations, found the equations already for yourself, just go ahead and extend it further. If you have not done that yet, please make those equations and make this short program. You know, you could use Python, or you could do it in MATLAB, do whatever. Just do this and see for yourself how different variables, as they change, how they impact the writability and readability of a memory cell. When you do this play, you know, when you play like this, you will have a much better understanding of designing the memory cell. So when you will enter into your project, you will be able to work on the project much better. If you don't do it, you will struggle at the time of doing your project. So better you do it. Okay. So now we come to the next part of this today's session, which is Rom cells. So we talked about Rom cells earlier. What was one thing that we established for the Rom cells when we were discussing Rom cells earlier?
So we were using different kind of layers, like the diffusion or the metal or the via to program them.
And what did we establish?
So that higher the metal layer, better better the time to market.
The higher the layer at which I do the programming, faster is the time to market, and therefore I prefer to do all my programmation at higher levels. At that point of time, there was a question about how do we program, and that is what we are looking at now. Okay. So let us say this is a memory, this is an array of devices where this is one row, this is another row, another word line, and there are all these nuances that are kept. The vertical purple lines are bit lines. Okay. But do you notice the bit lines are, the memory cells are not connected to the bit lines yet? Are you able to see that?
Yes, sir.
So what we do is we say that wherever I want to write a 0, that is wherever I want to discharge the bit line, at that place I will connect the transistor to the memory, to the bit line. At other places I will not. So what happens? This one would discharge, this one would not. Now the challenge is that there are some bit lines where there is, say, X number of connections. There are some bit lines where there are no connections. And there are some bit lines where every NMOS cell is connected to the bit line. Are you able to see this?
Yes, sir.
So do you want this kind of a situation for your bit lines, or do you prefer something else?
So what is the challenge?
First, have we understood what is the programmation being done here? How is the programmation being done here? Any questions about the programmation part?
So I'm not able to understand that.
The contact means writing 0.
Yeah, if I connect it to the bit line, I'm saying that I'm writing 0 there. The bit line would discharge. If I'm not connecting, Then when the word line goes on, the bit line would not discharge. So I've kind of programmed that cell to 1.
Right. Yes.
Okay. So we are doing that programmation, and over here what we are doing is some bit line, we are either connecting the bit line to the transistor or not connecting it to the transistor.
Sir, I had a doubt, sir, in the first column and the second column. In the first column, only the upper transistor is connected to the bit line. In the second column, both the transistors. So, but discharging would be taking place in both the bit lines. So, like, how will I distinguish this?
Okay, tell me one thing. When I select word line 0, let us say the bottom one is word line 0 and top one is word line 1. What will I read? Word line 0 पे अगर select करा तो?
Yes. Yes, sir. Yeah.
1 0 1 0 1 0 1 0. If word line 1 was selected, what would I read?
So above 0 0 0 0 1. Yeah.
So that is how we have programmed the memory there.
Yeah. Yes. Got it.
Okay. Now the problem is that over here every bit line has different capacitance. Every bit line has different capacitance. So how will you size your pre-charge circuit? How will you size your right driver circuit? Here's some columns, right driver, so there is no right driver in a ROM, but pre-charge is there. So some columns will get pre-charged very fast, others will not get pre-charged fast. Some columns will discharge very fast, others will not discharge fast. Let us say these two, let us consider these two columns. Okay. In these two columns, this has very high load on the bit line. This bit line is not that high. Suppose, let us consider two columns. In one column, say 90 cells are connected to the bit line, 10 are not. In the other one, let us say 10 cells are connected to the bit line. Now, I want to read a particular row where this cell is connected, but this is not. So what happens? This bit line will discharge to 0 very, very fast because the bit line capacitance is low. This bit line will remain at VDD. However, because its load is very large and there is so much leakage on it, it will fall a little. Okay. But there is this very fast moving another signal right next to it. It will cause it to fall further due to coupling. Okay. So we do not really want such kind of, you can actually analyze your design and you can arrive at what is the worst case for which you need to design. But the reality is on silicon, then there will still be many variations, many race conditions that will be there. We want to avoid that. If we want to avoid that, the same NOR cell, we program it differently now. What we say is all the NMOSes are now connected to the bit line. What do I program? I program the connection to the ground. So I am connecting some things to the ground, others there is no current path. So it is 0 0 1 0 1 1 0 0 on the top row and 1 0 1 1 0 1 1 0 on the bottom row. But over here the benefit is that the capacitance of all the bit lines is same. Are you able to see this? Any questions?
Sir, for example, in the earlier case, when they were not, we were contacting with the drain region. So in that case also, like with the worst case kind of that, we can basically design a circuitry, diode circuit such that only after that time only the signal will be generated.
Yeah, we can do that. I agree, Raghav. But it's still, while I can design the worst case, on silicon, I want as much symmetry and as much control as is possible.
Yeah.
With so many bit lines varying at different rates, it will be very difficult to debug if there is a failure on silicon. There are so many additional variables. Now, what is the capacitance? What was the code that was written? Because every chip will have a different code.
Yes, sir. Yeah, yes, sir.
You see, every chip will have a different code. So the number of variables that you have to handle in silicon debug, they increase overwhelmingly. You want to keep much more control with yourself. So you say bitline capacitance we maintain to be the same. Only the source side we now do the programmation.
Yes, sir. Yeah.
Okay.
Sir.
Yes.
Sir, previously we were programming it towards the drain position, right? Sir,
Yes.
so, sir, I didn't understand how the load is changing, sir, exactly on a bit line.
Okay, on a bit line, you have 10 source or drain regions connected, or you have 5 source or drain regions connected. Will the load change?
10 source or drain regions, 5 source. I mean, okay. So, sir, what I understood about load is that there would be a capacitance corresponding to the drain position of the transistor. That
Is there,
would,
wait, Vaishnav, is there a capacitance that is related to the drain and source region of a memory of a NMOS?
Yes, sir. In DVD, we have studied about that. Yes.
What is that capacitance?
Value is Kc. I mean, K into C.
No. We did something more also. We looked at the sidewall capacitance and the bottom capacitance.
Yes, sir. Yeah. Yes.
So there is a junction capacitance that comes into picture. Whenever you connect any source or drain region to any particular signal, that signal gets loaded because of the junction capacitance.
Yes, sir.
So the more the connections to the source and drain, the more the capacitance. The lesser the number of connections, lesser the capacitance.
Okay. So, sir, how did we overcome this that issue in this source connection, sir? While we are
You
connecting?
tell me. Look at any bit line. How many source regions are connected to it? How many how many transistor drains are connected to it? Is it changing across bit lines?
Oh, got it. Understood. Yes, got it.
Okay.
Yes. Thank you, sir.
Yeah. So this is the NOR cell. And NOR cell, what we are doing is we are selecting all the cells and we are selecting the cells, and wherever there is a what do you say, 0 written or a 1 written, depending on that, the bit line discharges. NOR cells are very fast. NOR cell based ROMs are very fast because there is just one NMOS there. But the problem is that they're not as dense. So we go to denser class of ROM memories, which are NAND memories. Now over here, we connect word lines. So we make a NAND kind of a structure. The topmost NMOS gets a clock, and the lower NMOSes get word lines. Okay. Now, suppose I want to read word line 0. I will keep word line 0 at low level. And I will, or wait, if I have to read word line 0, I will take word line 1 as 1, and I will maintain word line 0 at low level. Okay. So when the clock comes, what happens? When the clock comes, what happens? Will the bit lines discharge?
Word line 0 के drain तक discharge होगा.
Yeah. So the bit lines will not discharge. है ना? The bit lines will not discharge simply because word line 0 is off. Now, if I do the programmation over here, and the programmation is something like this. So when I keep word line 0 at 0, which columns would discharge? What would I read? Are you able to see this? Hello?
So it is basically NMOS stack completely, complete NMOS stack.
Yes, we have bypassed the NMOS through the programmation. We've connected the source or drain of the NMOSes where I wanted to write a 0.
Sir, and this connection should be dynamic, right?
Dynamic means?
I mean, it should be changing depending on the values which we want or the select lines which we
Yeah,
get.
so this programmation has to be done by the user. He says, I want to store this particular code in the ROM. I would know where it is a 0, where it is a 1, and I will then appropriately put the connections there.
Okay, sir.
So if I say that I am reading word line 1, so I will keep word line 1 at 0. I will take word line 0 high, and then I will bring the clock in. So what do I read over here? Are you able to see this?
So can you repeat this part again?
So when I wanted to read word line 1, I will keep word line 1 at 0.
Yes, sir.
Word line 0 goes high, and
Yes.
clock goes high.
Yeah.
What do I read? Now, even though word line 1 is 0, there is still a current path in this.
Yes, yes, yes.
I read 0 there. Now, because word line was 0, there is no current path here. So even though there is a current path here, and there is a current path here, I read a 1 there. Is that fine?
So how am I reading a 1 there? There is no current path in the third column, right?
Is there a path in the third column? My word line 1 is 0.
Yeah. Yeah, there is no one. Yeah. Yes, sir.
Okay. So I read 0011. So that is how ROM cells are designed. It is not that you just connect or program on source side or drain side and nothing would happen. You have to be very aware of the impact that your programmation can have on the overall robustness of the ROM. Okay. ROM cells are very dense. See, instead of 6 transistors of a memory cell, you have just 1 transistor per memory cell. So ROM cells are very, very dense, which means that there are huge coupling capacitances that will come between these bit lines. There are many other additional variables that can appear when there is a particle strike or anything, and that can really bother you. So you want to keep as many things in control and fixed. Even if that means larger power consumption, fine. Even if that means a little higher delay, you would say fine. But at least it is deterministic. It is in my control. Because there are so many other variables which will come into picture on silicon which are not in my control. So you want to keep as many things in your control. So you prefer to do source programming on the NOR ROMs than the drain programming. Okay.
So, for example, so he was saying that the bitcoin capacitance would obviously the interbitcoin capacitance would be significant because it is dense. But so, for example, if I'm storing a 0 here and it's going to 0, and on other side I'm going to store a 1. But since I don't have a connection there, so why would that be worrisome for me?
Because there is coupling happening between the 2 bit lines. These 2 bit lines will couple. So you had assumed that this bit line will not fall.
Yes,
you assumed it will remain at VDD. But due to coupling, it falls.
So, but where's the path to fall? I mean, still they need a bit.
Coupling हो रहा है ना, Raghav? What happens in coupling?
Okay.
What happens in coupling?
So I mean the capacitance kind of other capacitance will try to.
Yeah, 2 wires were running close to each other. You take one wire to VDD.
Yes,
what happens? You see the other wire also starts to rise a bit. That is what is coupling. Over here, you are discharging one of the bit lines to 0. So the other bit line, which was not expected to discharge, it's a floating capacitor, it will also discharge a little. It was supposed to be like this.
Okay.
Okay. So with ROM, you have to be extremely careful. ROM designs are not simple. It may appear that, oh, there is no right circuitry, so I have to design lesser circuits. But the circuits that you have to design are so dense that you have to be extremely careful that they remain functional even in the presence of these crosstalk and other capacitances and so on. Okay.
Yes.
So we will close here. We will start with the periphery circuit design in the next class. In the meantime, I would say those of you who have not done the equations, please do that. It will help you in your projects. Okay. We'll also come back to you with the project definitions, and you can check with the TAs in the office hours also. They can give you some hinters on what kind of projects to expect. Okay. So we close the class here. Any questions that you have? Any parting questions?
Sir, can we go to that VSS thing once again, if it's okay?
Okay, just give me a moment. Let me stop the recording, Samax, and then we do that. Okay. Let me
Yes,
close
sir.
the class. I will do separately for you. Anything else? Okay. Great, guys. Thank you. See you on Thursday then. In fact, I have my office hours tomorrow, so we could also meet tomorrow if you are, if you have some questions. Okay.